All right, welcome to today's explainer. Today, we're taking abstract algorithm problems and turning them into one unified, incredibly efficient strategy. You know that feeling when you're staring at a massive data set and your fingers just automatically start typing out a sorting function? Well, you might actually be falling into a pretty common efficiency trap. So today, we're diving deep into some fascinating source material from Idemann's AI journal, specifically breaking down the LeetCode heap pattern. We're going to completely demystify how this single data structure can become your absolute ultimate weapon for optimal efficiency. So let's kick things off with a little scenario. How exactly do you find the top 3 elements in an array of, say, 100,000? Picture this. Imagine you're a bouncer at a super exclusive nightclub. The club has a strict capacity. Only K VIPs are allowed inside. In this case, K is 3. Now, are you going to line up all 100,000 people outside, rank every single one of them from most to least important, and then finally let the first 3 in? No way, right? That is a massive waste of time. Instead, you just keep a running group of the 3 best VIPs. Every time someone new walks up, if they happen to be more important than the least important person currently in your VIP group, you just kick that lowest person out and let the new one in. And honestly, that right there is exactly what we're talking about today. Whenever we're faced with finding a really specific subset of elements, like the top K or maybe the kth smallest, the immediate temptation for most developers is just to use brute force sorting. You sort the entire array, which eats up O of n log n time, and then you just grab what you need. But in stark contrast, the heap pattern offers what I like to call surgical elegance. Instead of organizing literally every single element, a heap lets us efficiently maintain just the exact subset we actually care about. It saves a massive amount of compute time. Here is our quick roadmap for this explainer. First, the heap pattern explained. Second, conquering top K problems. Third, merging lists and matrices. Fourth, heaps as priority queues. And finally, number 5, the sorting trade-off. Okay, let's dive right into this. Section 1, the heap pattern core mechanics. Let's look at the engine of our hero data structure. So what exactly is a heap when we're talking about these coding problems? Basically, a heap is a data structure perfectly optimized to maintain a constrained size, which, again, we usually just call K. It does this by constantly popping out the lowest or highest frequency, or priority, element. Now, don't worry about getting bogged down in the syntax of binary trees right now. Just focus purely on the conceptual mechanics. Think of the heap as your dynamic bouncer. It efficiently processes a constant stream of incoming data, all while strictly enforcing that size K limit. I actually want to highlight this direct quote from the source text because it is an absolutely crucial rule of thumb. Quote, "The best data structure to find the smallest number among a set of K numbers is a heap." Seriously, whenever a problem asks you to find the top K, the smallest K, the most frequent K, or the closest K elements, this quote should immediately flash in your mind like a neon sign. This is your bold, memorable takeaway for spotting this pattern in the wild. Moving on to Section 2, conquering top K problems. Let's conquer our first major category by taking that rule and applying it to challenges like top K frequent elements and K closest points to origin. Let's compare approaches for the K closest points to origin problem. The brute force method, just sorting the whole list of distances, gives us O of n log n time complexity. Sure, we could use a min-heap of size n, inserting every single point, but that still takes O of n log n time and O(n) space. So we gotta ask the refrain, can we do better? Yes, absolutely. The triumphant winner here is the min-heap of size K. By immediately popping an item out if the heap size grows larger than K, we slash our time complexity down to O of n log K and our space complexity to just O of K. We literally only keep what we absolutely need. Now here's a super fun piece of insider coding trivia straight from the text that is incredibly practical. What if you desperately need a max heap, but you're coding in Python, which, as we know, defaults to a min heap? The pro tip is so simple it's brilliant. Just invert the sign of your sorting key, multiply your frequencies or distances by -1. Because when you push negative values into a min heap, the numerically largest original value suddenly becomes the smallest negative value, so it naturally rises right to the top. It's a fantastic, slightly sneaky little workaround. All right, Section 3, merging lists and matrices. Let's see how our pattern handles some of the more intimidating problems, like merge K sorted lists. And this brilliantly illustrates the exact step-by-step procedure for merging multiple sorted structures. Imagine you have K different linked lists, and they're all already sorted. First, you insert only the very first element of each list into a min heap. Second, you pop the smallest element off the top of the heap and add it to your final merged output list. Third, and this is where the real magic happens, whichever list that popped element just came from, you take the next element from that specific list and push it right into the heap. Finally, you just repeat that process. You never ever have more than k elements in the heap at any one time, which keeps your space complexity locked at O of k and your time at an efficient O of n log k. Which brings us to a slightly trickier beast, the kth smallest element in a sorted matrix. A matrix is tough, right? Because it lacks a straightforward middle index like a flat array has. Now, the source text outlines a really fascinating binary search approach that searches the number range, the actual minimum and maximum values, rather than searching the indices. But that requires counting elements and constantly adjusting your ranges. So the crucial point here is that while that binary search is definitely clever, you can completely sidestep all that convoluted logic by just throwing a min-heap of size k at it. By processing the matrix elements and maintaining that strict size k constraint, you get an incredibly elegant solution with consistent, predictable performance. Moving into Section 4, Heaps as Priority Queues, Scheduling Challenges. Next up, we are looking at scheduling scenarios where our standard arrays completely fail us. So think of a priority queue as a structure that stubbornly maintains its sort, no matter how many dynamic insertions or removals you throw at it. The course schedule problem introduces this really fascinating dual sorting conflict. You've got courses with specific durations, and they all have strict cutoff dates. Naturally, you want to iterate through time by sorting the courses by their cutoff date. But if you run out of time and suddenly need to backtrack to free up some space, you want to remove the course that ate up the most duration. So you need to sort by cutoff to process them, but sort by duration to remove them. This right here is exactly where a priority queue shines. As we process each course chronologically, we add its duration to our total and push it into a max heap. Now, if our total duration exceeds the current cutoff date, we don't just throw our hands up and give up. We look at our priority queue and we literally swap out the previously accepted course that has the longest duration. If the new course is a better, tighter fit than our longest course, we just drop the long one. This effectively frees up the maximum amount of time while keeping our total course count as high as possible. It's this backtracking logic that minimizes unnecessary insertions and perfectly tracks the optimal schedule for us. And finally, Section 5, the sorting trade-off, knowing the limits. Let's look at the minimum difference problem to see where our hero pattern finally hits a wall. Now, what's really interesting about this slide is the revelation that the heap isn't always the undisputed champion. In this specific problem, you're allowed to change 3 elements to minimize the difference between the maximum and minimum values. Logically, we only need to look at the 4 smallest and 4 largest elements. Using a heap to partially sort and just grab those 8 elements takes O of n log k time. But the source makes a super important point here. At a large number of moves, doing a partial sort with a heap actually becomes slower. When k gets large enough, the sheer overhead of managing the heap makes the standard O of n log n full array sort the faster, much more practical choice. But honestly, for the vast, vast majority of top k problems, O of n log k is your ultimate prize. By maintaining that strict constraint of size k inside your heap, you completely bypass the heavy O of n log n burden of fully sorting massive datasets. You keep your space complexity incredibly low, and you solve the problem with total surgical precision. So I'll leave you with this final provocative thought. The next time you're staring down a problem and you feel that immediate, burning temptation to just write dot sort, stop for a second and ask yourself, do I really need to organize everything, or can I just use a heap? By focusing purely on the key elements that actually matter, you are going to write much faster, far more elegant code. Thank you so much for joining me on this explainer. Keep practicing these patterns, and I'll catch you next time.